It's great to be here. I hope you guys are enjoying the school. I know I have been, and this is a fantastic place with a great vibe. So the title of the talk is the quantum mechanics of fluid and solids. So apparently I'm going to be talking about electrons moving on a lattice. And so far in this school, oh wait, I need to connect this. All right. Right, so far in this school, the lattice has been given a bad rep essentially because it provides those pesky Umklatt processes. It vibrates in the form of phonons and takes that precious momentum away from electrons, spoiling the high dynamic flow. But at the same time, it's clear that the lattice also provides the interesting part of the problem, right? It provides the interesting types of behavior of electrons. And actually today you'll see that often electrons flow through pipes in momentum space, okay? And this flow is pretty much unstoppable. Okay, so using Professor Falkovich language, I'm a different kind of plumber, okay? So basically, in order to establish basic notation for the problem, I will talk for a second about band theory of solids. And I cannot imagine that you have not seen, this stuff. But in order to establish the language, I have to do it. And actually, the spirit of very much the spirit of this talk will be a tutorial. Okay, so tomorrow we will get to more advanced topics, closer to the to where the research is right now. But today is just basically an educational kind of talk. So you very well know that electronic lattice is nothing but a periodic collection of ions, and these ions provide a certain potential through which an electron moves. Okay, so this motion is very much quantum mechanical. Okay, so electrons don't go bouncing around off each atom; they propagate coherently through the lattice. And the wave functions that electrons have on the lattice actually have a very general form that stems from the fact that Hamiltonian of electron on the lattice commutes with the translation operator on the lattice, so they can be diagonalized simultaneously. The translation operator has eigenvalues that have to be pure phases, otherwise you will grow or decay indefinitely as you translate your wave function. And basically all this can be summarized in the Bloch theorem that states that wave function of an electron on a lattice has this form. It's almost a plane wave. This factor you have seen many times, but it's a modulated plane wave. So the modulation part, periodic in the lattice, is given by this factor u. And you can imagine that since this factor is universal for any crystal, all the physics of the crystal, everything that you need to know about the crystal is actually hidden in this u. Okay, so finding this u is a big business, and there are local experts on this. Binghai Yan is one of the top people who can solve, Schrödinger equation of this form. Of course, he can do much more than that. Okay, but nevertheless, basically, if you take the Hamiltonian of the electron and lattice, I didn't put it down actually here, but the usual potential plus kinetic energy, solve the Schrödinger equation. What this procedure will give you is a set of energies, band energies, that correspond to every value of this quasi-momentum k, right? So there is a discrete set of levels for every k. These are bands. And the corresponding wave functions. You can formulate the problem for the full wave function, this, Bloch wave function, or you can, equivalently formulate the problem for this periodic part of the Bloch function with the so-called Bloch Hamiltonian, which is just the gauged version of the full Hamiltonian. Okay, so these two problems are absolutely equivalent because all the information about the crystal is hidden in U, as I said. Okay, so essentially the quantum mechanics of the electron is described by this equation. As any fundamental equation is tiny, once you get into details, it becomes super ugly, and of course there is gigantic technology developed to solve these equations. So A note in passing, this quasi-momentum K lives in a part of the momentum space called brilliant zone. All physically distinct states basically can be confined to this chunk of momentum space, and technically this brilliant zone is a torus, but this will not be very important for me today. Okay, so what can we do with this information that we get from this problem of solving the Schrödinger equation on the lattice? As I said, we get energies, band energies, and band wave functions, and there are two types of questions that we can ask. One has to do with so-called Fermiology, and it essentially has to do with the geometry of the isoenergetic surfaces in your band. Okay, the prominent example of the isoenergetic surface, of course, is the Fermi surface itself. So the studying the geometry of the surface has been the main subject of Fermiology for the past, I don't know, 70 years or so. And when I say geometry here, I really mean just the Riemannian geometry, where you study a surface, okay? So, Fermi surface of lead, of this, mono-element material looks like this. They're always some sort of a monster. So these circles that you have seen, of course, are not particularly realistic for metals, okay? So in order to get a feeling for the geometry of the surface, I could think, for example, about the curvature of the surface. And the way to get the curvature would be to use parallel transport. You know very well, I guess, from some course on differential geometry, that if you, say, take a vector, you drag it along a particular manifold, you impose the parallel transport condition, you do not let it rotate around the local normal, and you keep it in the tangent plane. If you go through a cycle and you get to the same point and the vector has rotated, you know that the surface is curved. Okay, it has curvature. Okay, and the geometry that I'm going to be talking about today has very similar flavor, except instead of some vector living in the tangential space, I will be talking about wave functions, and what I'm going to be dragging around is the phase of the wave function. So in particular, if I take my wave function, drag it through parameter space, which is the brilliant zone momentum space in this case, if I get to the same point and I accumulated a phase, I will say that my band is very curved, for example. Okay, it has non-trivial geometry. So this is the type of the game we're going to be playing today. So since it's a tutorial, what I would like to do is to establish some attitude toward this line of research. And in order to establish the attitude, I would like to use a quote by Michael Berry himself. So given that I'm on the record, I should say that I'm responsible for the interpretation of this quote, or misinterpretation of the quote. So it's from the book by Shapiro and Wilczek, a famous book on geometric physics in physics. And it goes like this. So the important part is this: many familiar problems that we do not ordinarily associate with geometric phases may be phrased in terms of them. You can kind of flip this statement and read it like this. There is a secret in this business. Like anything you wanted to do with geometric phases, you can do without them. Okay? And if Berry, Sir Michael Berry, tells you that you can do without Berry phases, you gotta take that seriously. Okay? But he continues and says that often the result is a clearer understanding of the structure of the problem and an elegant expression of its solution. So basically, it says that if you're not dead inside, you will like it, and you'll find it useful for physical intuition. And that is very much the point of view, I guess, that I want to take. And as you know, if you do this really well, you'll be awarded a Nobel Prize. I'm guessing this is a nice perk. Okay?
So I have a question.
Please.
So, for example, I'm sure that you have thought about this anomalous Hall effect.
Right.
You can formulate it without invoking Berry curvature, but there is something like intrinsic anomalous Hall effect, anomalous velocity of calculus and Latinger.
Mm-hmm. Right. We will go over this, of course. This will be a part of the presentation. Okay. So before we talk any quantum mechanics, any wave functions, let me formulate what we would like actually to correct. Okay, what is the purely classical description of electron dynamics in solids? So the classical formulation goes like this. So you take the band energy that you got from the solution of the Schrödinger equation, very much quantum mechanical problem. Okay, and you realize that in a crystal, electrons in external fields move actually classically, right? So external field is weak compared to, intrinsic interatomic field. It is smooth compared to interatomic fields. So the motion is largely classical. So you take the energy that you got out of the quantum mechanical problem and you promote it to the status of a classical Hamiltonian. Okay, so perhaps you couple it to vector potential using this minimal or chiral substitution in this context, maybe also electric potential. So you treat this as a classical Hamiltonian now. Okay, you write down the classical equations of motion. So the velocity ends up being just the group velocity derivative of energy with respect to momentum. The force, the rate of change of the quasi-momentum, is the electric field, the spatial derivative of the energy, plus perhaps the magnetic part of the Lorentz force, in which you substituted the usual velocity with the group velocity in that band. And then maybe you take these equations, you plug them into the left-hand side of the Boltzmann equation right here, and you solve the Boltzmann equation. Okay, of course, you have to supply the collision integral, which describes collisions of particles, which are quantum mechanical events. So today we will actually focus on the left-hand side of the Boltzmann equation, and tomorrow will be devoted to the right-hand side, essentially. So today we're sticking with velocities and forces in that equation. Okay. So how do we correct this classical picture? So, I gave you one slide course on solid state theory. Now it's a one slide course on Berry phases and adiabatic evolution in this type of systems. So what I would like to do basically is to construct this Bloch Hamiltonian that I promised will describe the Schrödinger equation, determine the Schrödinger equation for this cell periodic part of the wave function. Okay, so this is the Schrödinger equation we would like to arrive at. So the Bloch Hamiltonian is the gauged version of the full Hamiltonian on the lattice. Kinetic energy plus potential energy. You could have added spin orbit coupling and whatever you want. Okay, I just kept it in the simplest form for brevity. And what you end up with is the Hamiltonian that acts in the space of cell periodic functions. Now the boundary conditions are periodicity within the unit cell, which depends on k as a parameter. So p here remains to be a differential operator that differentiates wave function. K is just a number, a parameter. So now, when you take the first deviation from the classical picture, you have to, keep the classical picture in mind. So you subject your system to an electromagnetic field, which drags your electron through the momentum space. There is k dot, k changes. So this Hamiltonian becomes time dependent through the time dependence of k. And if this time dependence is not too fast, if the fields are not too strong, you should get away with still single level description. The adiabatic theorem of quantum mechanics tells you that if the dynamics is not too fast, you will stay in a given level during the evolution. So you take this propaganda essentially and try to solve the time dependent Schrödinger equation for the real wave function, given that instantaneous eigensystem. So this remains to be the instantaneous eigensystem with instantaneous energies and instantaneous wave functions. But what you're trying to find is the real wave function that comes out of the dynamics, of the full time-dependent Schrödinger equation. And given that you restricted your dynamics to a single band, which is governed by this adiabaticity parameter, the only thing that can distinguish this full wave function from the instantaneous one is a phase. So I separate here the usual dynamic phase, the integral of energy over time. Okay, so because this is boring, I don't want to be dealing with this. So there's extra factor which also has to be a phase. Okay, and basically plugging this form of the solution into the equation and projecting it back on the level with which we started, level n, you can get the following equation for the time derivative of this coefficient. Right, so it's time derivative is something times itself. This quantity is actually imaginary, so this is really a phase. Okay, the solution that you get is of this form, and then the quantities that enter here, gamma c and gamma b are the same things in these two equations. Basically have this form. So this gamma c essentially is a line integral along the path that you took in the parameter space, and what you integrate along this path is the Berry connection. Okay, so this is the connection. This is essentially will play the role of a vector potential and momentum space. Okay, so what you notice here, and perhaps you need to observe the following fact, that the time derivative of uk is the same as the gradient of uk in momentum space times k dot, that this phase, this gamma phase, c dot ends up being proportional to k dot. So, multiplying by dt, you see that the rate of change of k actually does not matter. It's a purely geometric phase that does not actually depend on how fast you go through momentum space. It only depends on the path that you took, okay? Which basically makes it a geometric object. Okay, fine. We found this additional phase that a wave function accumulates during adiabatic evolution. One objection you can raise toward this is that you always thought that phase does not matter. So wave function in quantum mechanics is defined up to a phase. So why would we care about this additional phase? The point here is that for an open path through parameter space, indeed you can absorb this phase into the definition of the state. But if you close the path, if you go to where you started, okay, if you accumulate extra phase, you can compare the final state to the initial phase state, and this phase you cannot actually gauge out. This phase becomes observable, okay? So this is the significance of this Berry phase, and the point is that it actually shows up in physical properties of a system. The first example that we will consider, one of the most famous examples, is the problem of Landau levels in graphene, or problem of semi-classical quantization of motion magnetic field in graphene. And I will break this problem into two pieces. I will consider classical dynamics and calculate the Berry phase quantum mechanically, and then we'll use that for quantization. Okay? This procedure actually is followed in any problem of this sort, except they can turn out to be much more complicated. So you know very well that graphene in its brilliant zone has two special points, 2k points. The other is time reversal counterpart of this point, and near the k point, the dynamics of the particles in graphene, dynamics of electrons in graphene, is that of massless relativistic particles. Okay, so except the speed of light, in quotes, is much slower than the actual speed of light. Okay, so you have seen all these cones many times, I'm sure. So the Hamiltonian that describes this particle near the cone is this two-dimensional Weil Hamiltonian, sigma dot k Hamiltonian, that's written out explicitly here. Okay. So I'm going to be dealing with the conduction band of this Hamiltonian with the, I guess, minority band in other terminology. The wave function of which is given by this expression, phi here, is the azimuthal angle of k. It's a direction, defines direction of k. Okay. So what happens classically? Of course, you know that classical motion in this case is just circular cyclotron motion. Okay. It's both circular in real space, and the radius of the orbit is the cyclotron radius related to the momentum of the particle. And it is also circular in the momentum space, right? So momentum also goes along a circle. Of course, magnetic field cannot change the energy of the particle. So particles always go along the isoenergetic contours here. Okay? So the relation between the two trajectories is established by the Newton's second law. The fact that dp by dt, the force acting on the particle, is given by the velocity cross b with appropriate, correction factor. So you can translate one trajectory into another. So this is the classical picture. But you see that quantum mechanically, we really do what we described in the previous slide, right? We take a particle and drag it through the parameter space, through momentum space. Okay? So we expect that if this is a non-trivial process, we can accumulate a phase. So indeed, since the wave functions depend on the azimuthal angle of k, only the azimuthal component of the Berry connection will be non-zero. We calculated taking the appropriate component of the gradient, get this 1 or minus 1 over 2k. So here the rotation direction is like this. So basically, I directed magnetic field into the screen in order to get a Berry phase of pi. I just wanted pi instead of minus pi. There is no really difference because everything is defined up to 2 pi as far as phases are concerned. Okay. So integrating this minus 1 over 2k over this circle, what I get is a Berry phase of pi. Okay? So the next question we ask is, so what? So what we do then, we try to quantize this classical motion. Of course, you know that if classical motion is periodic, in quantum mechanics there will be discrete levels that correspond to it. Okay? So I try to find these levels semi-classically. So in the, in atomic physics, that was called Bohr quantization. In this context, it's called Lifshitz-Onsager quantization. So basically what I do, I calculate the total phase accumulated over trajectory and equate it to, integer numbers of 2 pi's plus this, 1/2 times 2 pi factor that comes from turning points. Okay, this is Maslov index. You can formulate this problem as actually one-dimensional problem with 2 turning points. So the prescription is that you have to add, 1/2 to n. You know these things. You have seen these things in quantization for, harmonic oscillator, things like that. So the total phase accumulated by the particle contains 3 pieces. The usual, the first one is the usual classical action divided by h bar. It ends up being proportional to the area swept in the momentum space by pi p squared with appropriate correction factor that makes it dimensionless. Okay. The second piece again is a form of geometric phase, the Aronoff-Bohm phase. Right. You sweep a net flux in momentums in the real space. So you basically count that as a phase, which is given by the ratio of the total flux to the quantum of flux. Okay, again, this ends up being proportional to the area in momentum space. There is actually a minus sign here and the same correction factor. And then, of course, you have to include your Berry phase that you accumulated due to this evolution. And what you observe is that this Berry phase of pi exactly cancels the factor of 1/2 on the right-hand side. Okay, so what you end up having are energy levels. Okay, maybe I should say that in this case, of course, momentum is the same as energy up to a factor of 1 over velocity. So area in momentum space scales quadratically with energy. So you get a set of levels, relativistic Landau levels, energy of which is proportional to the square root of n. And what is notable about this is the existence of a level at exactly 0 energy. Okay, so for n equal to 0, there is a level with your energy, and when you change magnetic field, nothing changes to this level. Okay, for p squared over 2m, Landau levels, you know that the lowest Landau level is 1/2 of h omega c, and it goes up. It pushed out of low energy manifold by magnetic field. Nothing happens to this level. We will use this fact later on. So this is important to remember. I would agree with that, I guess, right.
Can I ask you a question then? So if I take you up on your challenge of the rephrased Berry statement, how would you get to this information without invoking the geometric phase interpretation that you just gave us?
No. So basically, I would just take, where is it? This Hamiltonian and would literally, look for the eigenvalues of this Hamiltonian. Of course, I will recover, this formula.
There's no equivalently intuitive, that's just a process, right? You would go through that process.
Yes, then that's exactly the point I am making, right? So formally I can get any result, but this kind of approach actually tells you where things are coming from.
And you say there's no equivalent approach that would also tell you where things are coming from?
Nothing comes to mind immediately. There might be something, but action I already wrote, right? Okay, so we talked about Berry phase, Berry connection. Let's talk about Berry curvature. So as with vector potential in real space, when you take curl of the connection, curl of the vector potential, you get some sort of magnetic field, some sort of field strength associated with that. We can play the same game in momentum space. We can take the Berry connection that we calculated, take its curl. That's the expression that we will get. Okay, so maybe I should make it explicit what's written there. What's written there is the following unit cell integral. So I integrate over the coordinates in the unit cell. I differentiate the wave function and sum over spin. So I take cross product. The cross product is between the vectors that are defined by the gradients. And I sum over spin, of course, and that's the essence of that expression that's written there. So by Stokes' theorem, the Berry phase that I introduced earlier can be calculated as as some flux of the Berry curvature. Okay, this is the same thing that you have seen in electromagnetism. So such defined barrier curvature has certain symmetry properties. It's fairly easy to show that inversion, if inversion is present in the crystal, it makes barrier curvature an even function of momentum. Okay, if time reversal is present in addition, it basically adds a minus sign in front of omega here. So it's obvious that if both inversion and time reversal are present, omega ends up being minus itself, so it has to be 0. So if you want a crystal with non-trivial barrier curvature, you have to break either inversion or time reversal. This is to be kept in mind. And the example of a system with interesting barrier curvature that I would like to stick with today is the so-called Weil semimetal. And Weil semimetal is more or less a three-dimensional kind of graphene. You will see, though, that this third dimension introduces non-trivial aspects of physics that are absent in graphene itself. So in other words, basically, semimetal is a minimal kind of deviation from a notion of an insulator. In an insulator, you have a full gap in the Brillouin zone, at least ideally. In a Weil semimetal, you allow a discrete number of band touchings, and you demand that these touchings are non-degenerate, not spin degenerate. So spin degeneracy is broken either by breaking time reversal, or spin degeneracy is broken by breaking inversion in the presence of spin-orbit coupling. Both of these ways will give you a spin-split band structure. Okay? So what you end up with is a band structure that looks like this. It's hard to draw it. So with graphene, it's easier because the K-space is two-dimensional. You can use the third dimension for energy. Here, it's K-space is already three-dimensional, so it's hard to draw in 4 dimensions. So you will have to live with this drawings that are not to be taken literally. Okay? So here I list the first few materials that were discovered. So actually the first materials were Dirac metals. They were essentially copies of these Weil metals put on top of each other and not being able to talk to one another. Okay? So these Dirac metals are like that. Okay, then people further discovered real Weil materials, and now the list is gigantic. There are reviews written on this. Okay, there is a couple. One comes from Bin Hai, actually, and Claudia Felser. So all materials, all this stuff is there, so I don't have to remember it anymore. So please consult the reviews if you would like to examples of either I or T or time reversal broken Weil semimetals. So what about barrier curvature in this Weil semimetal? So before I tell you what it is, I would like to rewrite the expression which we obtained earlier in a more suggestive way. Okay, so to do that, I insert a resolution of identity between these two functions. Okay, so this is, I sum over m and plug in here the resolution of identity. Okay, so you see I restricted the sum to m not being equal to n because you can see that the diagonal term basically does not make contribution. You take a cross product of a vector with itself, so you get 0, so m not equal to n. So I then use the following identity that can be derived from the Schrödinger equation directly. Okay, so the overlap of um with m not equal to n and derivative of u can be related to the matrix element of the velocity operator. dh by dk is the velocity operator. So if you take the diagonal element, you will get the group velocity. Of diagonal elements are just off-diagonal elements of the velocity operator. And this energy denominator. So if you take this and stuff it into the expression for the barrier curvature, you will get an expression like this, which does not look at all like this single bad expression that we had. And actually, if you started with the quantum kinetic equation, this kinetic equation with all bands taken into account, all band coherences taken into account, this is the expression you would end up with, which actually tells you that you're dealing with a case of interband coherence. You have this interband matrix element of velocity. This is one thing that it tells you. The other thing that it tells you is that if you want to look for places with large barrier curvature, you gotta look close to band degeneracies, right? These small energy denominators will make barrier curvature large in general. Okay. Of course, in Weil semimetals, this situation is on steroids, right? You have band touching, so that's the largest you can get, more or less. Okay. All right, so also this is the expression that is used for practical calculations because this one is horrible for that, right? If you use Mathematica to solve for UK, with subscript k, in general, it'll spit out some vector with random phase attached to that vector. So if you want to differentiate it, you will suffer a lot. So instead, of course, you would prefer differentiating the Hamiltonian, which you know presumably. Okay, that's the Hamiltonian to get this wave functions from. So this is also a practical formula for calculations. Excuse me. So by using the three-dimensional version of the Weil Hamiltonian, I will not go through this exercise, but you will believe me, this is the case, right? So you have this, energy denominator squared here, and of course the energy difference here scales with k, so you get k squared in the denominator. So you get this form of the Berry curvature. Again, this is for the conduction band near the Weil point that resembles very much a field of a monopole, right? 1 over r squared directed along r. Okay. So immediately know that if you take this Berry curvature and take the divergence of it, you will get something with a delta function on the right-hand side. So you have to be careful here because a potential field of a monopole has this 1 over 4 pi in it. So I have to divide by 2 pi to get 4 pi here, multiply by 2 pi. This is the origin of the 2 pi. Okay. Other than that, basically I generalized that expression to introduce the Berry charge associated with the Weil point. So this Berry charge basically coincides with the sign of V. Okay, Berry curvature is one sign for conduction band and opposite sign for the valence band. It changes sign for a given Weil point. But this Q, it essentially defines the chirality of the Weil point. In a more general case where V is a matrix connecting sigma to K, Q is the sign of the determinant of V. So, and I choose Q to be positive if determinant is positive. Okay. So, and then the delta function is also a little bit written a little bit differently. So here I counted k from the Weil point. Here I make this difference explicit, right? So kw is the location of the Weil point in the Brillouin zone. So k is counted from this, capital K, right? So essentially, Weil points in the Brillouin zones are the Berry charges located in the Brillouin zone, and they are sources or sinks of the Berry curvature. Okay. So this is the topological aspect essentially of the Weil semimetal physics. Okay, so we talked about Berry curvature. So what's the big deal? Now we get to applications, to anomalous Hall effect and whatnot. Okay, so the non-trivial part of this is that these Berry curvatures show up in semi-classical particle dynamics. Okay, they determined where particles are flying and with what velocity. To appreciate that, let's calculate the operator of a coordinate in band representation. So if I want to describe the dynamics of a particle, at least I need to know where it is. Okay? So let me calculate where it is. So what does it mean to calculate operator in some representation? So wave function in band representation is given by this expression. Okay? So this is the basis of the representation. And C and K, the coefficients, are the wave functions in that representation. So I need to know how R operator acts on this wave function. So the like a 2-minute derivation of this goes as follows. Of course, R acting on the basis is just by multiplication. So I write R as the derivative with respect to K of this exponential. Okay, and then using integration by parts, I move the differentiation onto everything else, onto C and U. U has to be differentiated because it's K dependent. Okay, so I get an expression like this. I have to differentiate both C and U. And then I recognize that U is a cell periodic function. Derivative with respect to K of a cell periodic function is also a cell periodic function. So I can re-expand this derivative in the basis of this, all states at given K, cell periodic states at given K, except I do not want to do that. I want to project on the same band. I want to stay within the same band. So essentially, I project this back onto UK. There is a bracket here, closing. And what I end up with is expression like this, right? So I end up with the same basis vector that I started with. And there is something that acts on my coefficient, on my wave function, and that something involves the differentiation operator and some extra piece, which turns out to be nothing but the Berry connection in this band. Okay? So let me rewrite this. Let me restate this. R essentially is the usual piece that you would expect from usual regular quantum mechanics plus a little bit. And the meaning of these terms is as follows. Remember, I told you K lives in a finite chunk of the momentum space in the Brillouin zone. So basically, it tells you that it's conjugate to a discrete variable. Okay? So this part of the operator is essentially the lattice coordinate. This tells you where the particle is up to a unit cell. And this piece tells you where the particle is in the unit cell. Okay? So another lesson to be learned from this is that since the position of the particle depends on its momentum, if you change momentum, you change position. If you scatter the particle, it shifts. If you move the particle, it shifts. And this is the origin of all these anomalous effects that you encounter in this business. Okay? So let's put this to use. So there are ways to derive all this, of course, except they take time. So I will proceed by analogy. So I now write down the expression for the operator of momentum. Okay, so this is the physical kinetic momentum, which is the canonical one minus the vector potential. And I see that now the operator of coordinate has the same kind of structure, right? It looks like a vector potential in p space. So I expect the same symmetry in the equations of motion for the two quantities. And what I get is the following. So the equation for p looks unchanged. I have the electric field here, and then magnetic power of Lorentz force, velocity crossed with b. And in the equation for r dot, I get the group velocity plus this Lorentz force in momentum space, right? Which is a cross product of the velocity in momentum space and magnetic field in momentum space.
These equations are classical, right?
They are semi-classical. So the order of these corrections is h bar. Yes. So
Only this term, but
right.
the Lorentz force in different case.
You see, they're kind of mixed because it's r dot, not d epsilon by dp. So there is actually a piece that is also h bar hidden there. Okay.
Before you said that you can see the phases only if you do interference experiment. Now you are saying basically that you'll see it even in semi-classical trajectories that do not interfere with themselves.
I mean, in a sense, once I told you that it is the Berry curvature that enters, it is some sort of closed loop that is lurking behind. Basically, I already dragged it through a small loop and saw that there is curvature.
So interference on the scale of the.
Right. Yeah. Exactly. Yeah. Exactly. Okay. Okay. So let's apply this to something. And the first application I will talk about is the anomalous Hall effect. So you know what Hall effect is. Okay. So anomalous Hall effect is the same thing, except instead of magnetic field, you use magnetization. So one thing you should appreciate here is the timeline. So the anomalous Hall effect was discovered by the same Hall 2 years after the regular Hall effect. Okay, so it took some 70 years for Karplus and Luttinger to figure out that it was related to the spin-orbit coupling. Okay, in the band structure. In the hindsight, it's kind of obvious because magnetization lives in spin space. Current that you want to get lives in the orbital space. So there should be spin-orbital coupling that relates the two. But it took 70 years to figure that out. It took another, almost 30 years to kind of place this in the context of geometry, okay, by Thouless and collaborators, okay. Essentially, what we're going to derive is this, TKNN formula, okay. So what you can compare it to is to timeline of the, superconductivity in BCS, which only took 40 years to start, hooking with gas and figure out everything. So apparently, what took us, some few minutes to do is quite difficult actually historically. Okay, nevertheless, what I would like to do now is to take the equations that I derived, drop the magnetic field term in it. Okay, so I want to get a Hall effect without magnetic field, and then what I end up with are equations where only velocity is modified by this anomalous velocity term. In order to calculate current, I just take this velocity, multiplied by the probability to have a particle with such a momentum, right, by the distribution function, occupation number, and integrate over all occupation numbers. Okay, so this is my prescription. What I get out of this is the Hall conductivity. Obviously, this current flows perpendicular to electric field. It feels like this is almost like magnetic field, except it's built out of Berry curvature. So it is some sort of Hall effect. And this is the Hall conductivity, or rather anomalous Hall conductivity. So I can proceed and calculate this anomalous Hall conductivity for my precious Weil semimetal. The exercise is very simple. So let me take a particular component of the Berry curvature, omega A, and rewrite. Here basically I'm assuming that I have a filled band. Okay, so you see that here I killed the distribution function for a second. I will talk about it later. I assume that I have one filled band, so f basically is 1 for that band. I only need to integrate the Berry curvature. So I integrate a component of the Berry curvature. I rewrite it identically as omega b times delta AB, Kronecker symbol. And then I rewrite this Kronecker symbol as the derivative of k with respect to k. This is an identity. And this derivative I integrate by parts. Okay, so I move the derivative onto omega and flip sign. So what I end up having is the divergence of omega multiplied by k. So remember that divergence of omega comes only from the monopoles. Okay, so what I'm doing here, essentially I am going from monopole to monopole and multiply its charge by the location in the brilliant zone of that monopole. So what I end up having is the dipole moment of this, Berry charges in the brilliant zone. There is a caveat. This integration by parts is not harmless. The boundary term here is non-trivial, but you can show that the boundary term, which comes from the brilliant zone boundary, essentially makes this Berry curvature monopole defined up to a reciprocal lattice vector. Okay, so this k vector is defined up to a reciprocal lattice vector. Okay, so there are many important papers written on this expression and this line of formulas, but I guess the first paper that does that carefully is PRL by Haldane from 2004. Okay, so all these boundary terms are discussed there, and also I think it's shown there that even though this looks like a Fermi C term, you can rewrite it as a Fermi surface contribution. There was some controversy with that. So let me comment about the Fermi surface. So in wild semimetals, you know that the chemical potential is never at the location of the node. Okay, so the question is, what am I doing here? So the point is that this expression survives if the individual Fermi pockets around individual nodes are time reversal symmetric. If I count k from the wild point and k is the same as minus k, time reversal symmetry is preserved, then this is the expression, this is it. If this is not the case, and there is no physical reason for that to be the case, tilt or any kind of perturbation will deviate from this time reversal symmetry, there will be actually Fermi surface contributions to this formula, but typically they're actually small. Okay, so this nevertheless can, this almost quantized Hall effect, it's quantized up to some brilliant zone vector, actually some random brilliant zone vector, or not random but non-special brilliant zone vector, can give the largest contribution to anomalous Hall still in this situation. Okay, even though it's not protected against Fermi surface contributions that can actually come from disorder too. So we're talking about intrinsic Hall effect here. Okay, but enough about Hall effect. So what I would like to now do is to switch to the situation with magnetic field and see what these equations of motion, the semi-classical equations of motion, give me when I do include magnetic field. So what you see here is that the p prime and r prime are kind of mixed into this right-hand side. So what I would like to do is to solve for p prime and r prime. I would like to have things without dots, without dots on the right-hand side. So if I do that, what I will get is R2 expressions like this. Okay, let's look at the force first, p dot. There is this factor 1 over dB. Basically, this is the famous density of states factor, and eventually it comes from the fact that p and r are not a canonical pair. Okay, so they're a physical observable coordinate. They are not canonical, and that's why you have this factor of d floating around. The important property of this factor is that it always disappears. Okay, so it somehow kills itself if you do everything properly. So do not look at this d. I just put it there for consistency. So in the force, you get the usual Lorentz force, electric magnetic component, but you also have this weird piece with E dot B product and directed along the Berry curvature. And we will see soon that this is the origin of so-called chiral anomaly. This is the flow through momentum space pipes, essentially. This is the chiral anomaly. So in the expression for the velocity, we have now a familiar term, the anomalous velocity, okay, which describes anomalous Hall effect. We're not gonna talk about that anymore. We covered that. But also there is a anomalous velocity essentially driven by magnetic part of the Lorentz force rather than the electric one. Okay, this is also sort of anomalous velocity. You see that it's weird. It's directed along the magnetic field. All of a sudden, particles start to fly along the magnetic field, even though there is no Lorentz force to push them to fly in that direction. Yet they get velocity along the magnetic field, and this velocity describes so-called chiral magnetic effect. So my plan for the time remaining is to describe first chiral magnetic effect, then chiral anomaly, and then show you the relation between the two. Okay? Obviously, they both come from Berry curvature. Okay, chiral magnetic effect. So chiral magnetic effect is a name for a current that flows along the magnetic field. Okay? So the chiral, basically, the word chiral comes from the fact that this is a vector, polar vector. This is a pseudo vector, axial vector. So if you have one proportional to the other, you must have inversion broken in your system. Okay? So there should be chirality associated with that system. And magnetic, because I guess there is magnetic field involved. Okay? And effect, because something is happening. All right? Okay, so I take this current, plug in the part of the velocity that is of interest to me. Okay, I get this expression. Okay, and that's my current. So again, this expression looks very much like the Fermi C current. So it looks like all these field states in my band structure contribute to that current. It's actually an optical illusion. So what I would like to do is to rewrite it as a Fermi surface contribution, which will have sort of pedagogical implications. So the way to go between Fermi C and Fermi surface contributions is integrating by parts. This actually, the way not to make mistakes in this business is just to integrate by parts properly. Okay, so if you can do integrating by parts, you're going to be golden. Okay, so the way it's done here is as follows. You recognize that velocity is the gradient of energy in the momentum space. I apologize. I use P and K interchangeably. K is more appropriate here because I'm suppressing H bar, so I should be talking about wave number, but I always slip into writing P somehow. P is more natural to me. So, if you see P or K at this point, they're the same. Okay, so this is just the gradient of energy. So I plug this expression here, integrate by parts, and I get two terms. I have to integrate Berry curvature, and I get the divergence of the Berry curvature in momentum space, and of course I have to differentiate distribution function. So this term, even though it still looks like Fermi C, it's an identical zero. So the way you can see it is as follows, that this term again is non-zero where you have Weil points, and at Weil points two bands meet. These bands have the same energy, they meet there. They have the same occupation for the same reason. But the Berry curvatures are opposite. So the sign of the divergence is opposite. So actually, when you sum over all bands, this thing disappears. And what you end up with is
argue that omega is a curl and so divergence of the curl is zero.
This is the usual issue with monopoles, right? So the field of a monopole has zero divergence everywhere but at the monopole. That provides for ambiguous vector potentials, but you have to live with that. Okay, so the only thing remaining then is the term with differentiated Fermi function. So obviously this is non-zero only where occupation changes, where there is a Fermi surface. Okay, so it's a Fermi surface term all of a sudden. And I will show this later basically, but this term, except for this energy, essentially counts the Berry charge inside the Fermi surface. I intend to show this more explicitly later on when we talk about chiral anomaly. But again, what you end up having here is essentially sum over all Weil points. And what you have to sum is the chemical potential. You trade energy essentially for the chemical potential. The derivative changes epsilon into mu. So you sum mu times the Berry charge of the Weil point. Doesn't matter conduction band, valence band, it's the chirality of the Weil point. There is no ambiguity at this point. Okay? So what you see in this case, let me go back to the case of Weil semimetal where this chiral magnetic effect has a chance of happening. Basically, if you have a few Weil points that are filled to different chemical potentials, you will have a net current that flows along the magnetic field. And I guess the first person to notice such a current was Vilenkin in 1980, except he talked about a chiral vortical effect. We'll talk about chiral vortical effect tomorrow. Okay, so chiral vortical effect is response to angular rotation rather than magnetic field, but this is more or less the same thing, right? Symmetry-wise, omega omega rotational frequency is the same as B. So this tells you two things. That you have this current if chemical potentials are different, and it also tells you that you have exactly zero current when chemical potentials are the same. Okay, so there was a bit of a controversy in this business because in a crystal, while points, of course, sorry, all this was discussed in the context of high energy physics, right? Where maybe Vilenkin thought about neutrinos, and Lorentz symmetry will make will put all while points at the same energy. In a crystal, if while points are not related by symmetry, they can be at different energies. So it's very tempting to say that, look, even although chemical potential is common, counted from the common origin is common, it looks like the doping level counted from the while point is different. So maybe in this case we will get the an equilibrium current that flows in equilibrium, but just is proportional to the difference in energies of the two while points. And there were mistakes made along these lines, but they're kind of almost forgivable, because this current proportional to the field in equilibrium passes almost all tests except the test of gauge invariance. So for example, this is time reversal odd, this is time reversal odd, so the linear relation between the two does not break time reversal, so maybe it's a non-dissipative current that can actually flow in the ground state. Okay, so this is a polar vector, this is the axial vector, so linear relation between the two requires broken inversion. But that's how I got these points at different energies in the first place. I broke invergence, also fine. So what actually breaks down is the fact that you can show that if there is an equilibrium current, equilibrium is important, proportional to B, there is actually a magnetization proportional to the vector potential. This fact was noted in a paper by Levitov, Nazarov, and Eliashberg, actually quite a bit before these two papers, which showed that it's zero for the particular case of wild semimetal, and I hope this is more or less the argument in that paper. Okay. Okay, so it turns out that actually this zero pertains only to equilibrium, so you can go away from equilibrium, you can apply magnetic field at finite frequency. And then you will get this dynamic chiral magnetic effect. And for a particular model, this effect was considered in these two papers. Actually, in this paper too, except here it came from impurities, not from band structure. Here, this dynamic chiral magnetic effect came from band structure. And then, my student and I, Jing Ma, who is now a postdoc with Justin Song, and then, Joel Moore's group, in collaboration with Ivo Souza, basically calculated this dynamic current for arbitrary band structure. It turned out that it had nothing to do with Berry curvature. It actually is determined by magnetic moments in the band structure. So I will talk about these intrinsic orbital magnetic moments tomorrow when we talk about chiral vertical effect, but I will not talk further about this business. Okay, but just know that it's been done. Okay, so just a few minutes for chiral anomaly, I guess I will stop. So chiral anomaly comes from the equation for the force, as I described. So basically what I would like to do now is to see what kind of effect this weird term in the force has on the dynamics of particles near a while point. So what I do essentially is I take a kinetic equation for a given point. You have seen these things before. And I keep the usual time derivative. I drop the spatial derivative term. It's not important right now. I only keep the field drive. And in principle, I can put there the intra-valley collision integral. So I do not allow electrons to get scattered to other valleys, because I don't want to have this kind of non-conserving processes. Okay, but inside the valley, they can scatter all they want. Okay, and then what I would like to get now is an equation for the charge density in that valley that I consider. So in order to do that, again, I use the expression for the charge density in the valley. I have to correct the density of state by this precious d factor, which again kills the 1 over d in the expression for p dot. Again, they always disappear. It's almost tempting to just forget about them, but it's scary because what if they there is one time that they don't disappear. Okay, so basically what we get is the following. So the e dot b term you can pull out of this integral, of course, and what you end up with is the integral of a Berry curvature with a momentum derivative of the distribution function. Using the equilibrium form of the distribution function, you can rewrite it as the essentially a Fermi surface integral. And given that I'm running out of time, I will not show that explicitly, but maybe I will include this in the posted version of the notes, so you can see this at least once in your life. Okay, so what this integral does, again, it just counts the buried charge inside the Fermi surface. So what you get here is this E dot B term with the same 1 over 4 pi squared coefficient that we had in the chiral magnetic effect case, and again the buried charge in front. So you see that basically this term makes the charge near wild point not conserved. And this is the origin of the word chiral anomaly here. So was there a question? So if you looked at the classical equation of motion for the fermions living near this wild point, you would see that they are described by purely decoupled Dirac equations, essentially. However, when you consider quantum mechanical response, you see that there is actually this chiral species non-conservation, and that's where the word anomaly is coming from. Basically, you have classical conservation law broken at the quantum mechanical level, hence the name. Okay. So this charge non-conservation again then has the name of the chiral anomaly. You can notice that it comes from the same kind of integral that involves buried curvature. And should I stop at this point, or a couple of minutes? Just the last point I will make then is that all these results can be very easily interpreted based on the Landau level picture in this problem. So instead of using the semi-classical corrections to dynamics, we can solve for the exact levels in magnetic field and see what they correspond to. And what you do is you basically notice that this problem of a wild node is essentially identical to the problem of graphene with a mass that depends on Pz. Okay? So now forget about Pz for a second. Put it to 0. Pz is a long B field. Okay? So you have graphene in magnetic field. We derive the Landau levels for graphene in magnetic field. You have the 0th Landau level and the square root of n levels that sit there. So when you turn on the gap, these non-zero levels kind of disperse normally. They stay within the valley. And the 0th Landau level that used to be at 0 becomes chiral. Right? It runs chirally. So in a crystal, these guys actually join together, these two chiral levels. They join together somewhere deep in the band. Okay, then it's clear what happens when you turn on electric field. Sorry. When you turn on electric field along the magnetic field, what you do is you have these electrons accelerating, right? They increase their momenta. And if you blind to the bottom of the band, you see that they seem to be appearing out of nowhere, right? This is this anomaly term that kind of pulls this low energy charge out of nowhere. However, of course, in this valley, they get decelerated. So it looks like they're disappearing into nowhere. Of course, these two processes, balance each other. The net charge is conserved. This E dot B term kind of makes charge flow from one valley to another. And this process basically does not even stop if you put impurities in the way of these electrons, and that is ensured by the probability conservation and scattering. Okay, so you have to forget about momentum as the quantum number in that case. However, if you do not allow scattering between this valley and this valley, you have 3 modes going up, 2 modes going down. No impurity can repackage 3 electrons into 2 electrons. So this one extra mode will keep going no matter what you do. Okay, unless there is a way to take this mode and kind of make it make a U-turn into the other valley. Actually, surface can do it, for example. All right. So this is the picture of the chiral anomaly, just the pushing between the two valleys. Chiral magnetic effect essentially is the same. Right now, you recognize that if you take different chemical potentials in the two valleys, okay, you have more, say, positive movers up the field than you have movers against the field. And this imbalance, given by the chemical potential difference, translates into a current proportional to the chemical potential difference, and that's with exactly the right coefficient, of course, and that's the chiral magnetic effect that we saw before, that we obtained from the semi-classics. So let me stop here, and what I will start with tomorrow is the transport theory for these electrons. I will talk what kind of observable phenomena actually come from this chiral magnetic effect, chiral anomaly, and then we will switch to things that are more related to hydrodynamics, that are related to collisions and related effects. So I'm done. Thank you very much.
So, Dima, I have a very general question. You see, this passage from the quantum mechanical picture to semi-classical picture. First, you are discussing block waves. That's where the whole Berry curvature appears. When you use Weizmann theory, you are imagining that you have wave packets, quasi-particles at the Fermi level. This becomes very important when you do your experiments at, let's say, 1K. Normally, you can forget anything which is happening, which is a distant, like a few microelectron volt out of the Fermi surface. You see? So the question is, so this debate, you talked about it, but very, very briefly, did Fermi surface versus Fermi sea debate is very important, because the whole question is, shall we worry about while nodes which are far from the Fermi surface, deep inside the Fermi sea? Can they have, any kind of visible effect? How do you do it? When you write a semi-classical expression for transport, you are imagining that you have quasi-particles. But the Berry curvature is deep inside the Fermi sea. So,
I mean, in principle, I have nothing to add to what you already said, right? So the transition, of course, is accomplished by constructing the wave packet. So if you can construct wave packet that is large on the scale of lambda Fermi but small on the scale of the field, this works. Okay, so the magic of Fermi surface versus Fermi sea in this particular case comes from charge conservation, essentially, right? So forget about this part, right? You have this sausage of electrons flying up. Okay, of course, if you take half of the brilliant zone, you have this current that is carried by all electrons. What makes it a Fermi surface contribution is that the fact that there is almost canceling current carried by the other half of electrons. But this is primitive logic, right? I mean, I could do this in one dimension. And of course, in a one-dimensional case, if I fill one branch to one chemical potential and another branch to a different chemical potential, only the difference is what matters, even though there is counter-propagating current in the Fermi sea. So, it's just a counting problem, if you will.
So
there's no magic here or not anything particularly deep. Integration by parts is important, that's it.
So exactly, so integral by part. What happens if you have disorder and there is a elementary pixel in K space below which you cannot go?
I mean, at that point, you have to invoke basically charge conservation. That if you have this net current that goes up, in this mode, if you do not scatter between the two branches, if there's no back scattering, it's unstoppable. So you can make this branch, I don't know, go slower, but then you will increase the density of state. It will compensate that slowness, so you will have the same current. And even you can do away with non-p. P does not have to be a quantum number. Once you write the transport equations, I will do it tomorrow. You don't care where they came from, p space or what it came from. You just have current that is proportional to magnetic field and with some coefficient. Okay, so that doesn't lead to any difficulties. I mean, there is probably some smart but unnecessarily complicated way of deriving it. There is this Bott index that is the analog of the Chern index for disordered systems, and probably you can go that way. But why would you? I mean, if things are so simple.
One question.
Dima, if I use the way that we like to interpret our anomalies is that we need to sacrifice one symmetry to save another. Can you explain chiral anomaly of your case?
This is the high energy way, right? So there is no here there is an explicit regularization in the bottom of the band, right? I know which one is good symmetry. In that case, you would say, okay, I want the charge to to be conserved, so I will kill the axial symmetry. But here I have everything regularized. So
total charge versus charges in separate terms.
Yeah.
If not, let's then Dima.
Right.